Today in the surface chemistry, we will discuss catalysis. You know what is catalyst? Catalyst is a substance which can alter the speed of a chemical reaction without involving itself in the chemical reaction. That is a catalyst. Catalyst can usually increase the speed of a chemical reaction, but it will not take part in chemical reaction. And the increase in speed of a chemical reaction by the use of catalyst is known as catalysis. Berzelius in 1835 suggested the term catalysis. There are two types of catalyst: homogeneous catalyst and heterogeneous catalyst. And usually these catalysts work with the in presence of, or for the working of proper working of catalyst, catalyst promoters are required. And in order to deactivate the catalyst, we require poisons, promoters and poisons. Promoters are substances that enhance the activity of a catalyst, while poisons decreases the activity of a catalyst. Promoters that will increase the activity of a catalyst, ability of a catalyst to increase the speed of the chemical reaction, while poisons decrease the activity of a catalyst. It is required sometimes. For example, hydrogenation of alkynes. Alkynes, if you want to limit it at the alkene level, we have to use catalytic poisons. In Haber process, manufacture of ammonia, molybdenum acts as a promoter for iron, which is used as a catalyst. Example for promoter, molybdenum. In the process, Haber process, it is the promoter of the catalyst iron. Now, what is homogeneous catalyst? When the reactant, products, and the catalyst are in the same phase, the process is said to be homogeneous catalysis. Reactants, products, and catalysts all are in the same phase. Examples: lead chamber process for the manufacture of sulfuric acid. Here sulfur dioxide reacts with the oxygen to form sulfur trioxide in presence of nitric oxide. You see the physical state of reactants, products, and catalyst. All are in gaseous state. SO2 in gaseous state, which reacts with O2 in gaseous state to form SO3, sulfur trioxide, which is also in gaseous state. And what is the physical state of the catalyst, nitric oxide? Gaseous state. Hydrolysis of methyl acetate is catalyzed by H+ ions. Another example: CH3COOH plus CH3OH gives CH3COOH thrice, CH3COO CH3 plus H2O in presence of HCl. So here if you analyze, you can see CH3COOH is aqueous solution, which is in liquid state. CH3OH also in aqueous solution, which is in liquid state. HCl is a liquid. CH3CO CH3 also a liquid. H2O is a liquid. So all are in liquid state. Hydrolysis of sugar is catalyzed by H+ ion furnished by sulfuric acid. Another example: C12 H22O11 plus H2O in presence of H2SO4 gives C6H12O6 plus C6H12O6. Here glucose, aqueous solution of glucose, dilute aqueous solution of glucose is taken. H2O is a liquid, H2SO4 is a liquid, glucose and fructose, their aqueous solutions are obtained, so all are in the same phase. Now the second one, heterogeneous catalysis. It is common, very common catalysis. All of you are familiar with the Haber process, Ostwald process, and contact process. Contact process for the manufacture of sulfuric acid. Here, the reactants, products, and catalysts are in different states. Reactants and catalysts are in different state. That is heterogeneous catalysis. Reactants and catalysts are in different state. So here in conductor process, you can see 2SO2 plus O2 gives 2SO3. All these are gases, but the catalyst is vanadium pentoxide V2O5, which is in solid state. Haber process, N2 plus 3H2 gives 2NH3. All these are in gaseous state, but the catalyst is in solid state, Fe2O3. Ostwald process for the manufacture of nitric acid. In this process, 4NH3 plus 5O2 gives 4NO plus 6H2O. All are in gaseous state, but the catalyst is in solid state, platinum. Hydrogenation of vegetable oils in the presence of finely divided nickel as catalyst. Another example. Finely divided nickel is in solid state, and the vegetable oils are in the liquid state. And after hydrogenation, it will be changed into vegetable fats. That also will be in the solid state. Now, what is the theory of catalysis? We have to study the theory of heterogeneous catalysis only. There are different theories for heterogeneous catalysis. Adsorption theory of heterogeneous catalysis. What is absorption theory? Reactants in the gaseous state or in solution are adsorbed on the surface of the solid catalyst. So when it is absorbed on the surface, the concentration will increase on the surface. Therefore, a reaction will take place at a very high speed because of the increase in concentration. When all the reactants are absorbed at the surface of the catalyst, it is present in a very small area. Therefore, the concentration will be high. Therefore, the reaction will take place at a faster rate. The heat of adsorption is utilized in enhancing the rate of the reaction. We know most of the reaction increases with increase in temperature. So during the reaction, if heat energy is liberated, that also can be utilized in order to increase the speed of the chemical reaction. And adsorption, already we mentioned, it is an exothermic process. Surely heat energy will be produced. Intermediate compound formation theory, that is another theory. The reactants and catalysts combine to form an unstable intermediate. An intermediate compound will form. And which on decomposition gives the product. First catalyst combined with the reactant to form an intermediate. But we have to study the modern theory of adsorption, that is a combination of these two, adsorption theory and the intermediate formation theory. The mechanism involves 5 steps. According to modern adsorption theory, the mechanism of catalysis involves 5 steps. The first one, diffusion of a reactant to the surface of the catalyst. Reactant slowly comes to the surface of the catalyst. Second, adsorption of reactant molecules on the surface of the catalyst. Reactants are adsorbed on the surface of the catalyst. Occurrence of chemical reaction on the catalyst surface through formation of an intermediate. Then it will react with the catalyst and form an intermediate on the surface of the catalyst. Desorption of reaction products. So if it is adsorbed on the surface and if there is chemical reaction, what is the result of chemical reaction? That will be product. So in the next step, desorption of reaction products from the catalyst surface and thereby making the surface available again for more reaction to occur. So the products formed on the surface of the catalyst, that will be desorbed from the surface. And in the 5th step, that is final step, diffusion of the reaction product away from the catalyst. But it has a problem. It does not explain the action of catalytic promoters and catalytic poisons. How the catalytic promoters are acting or how the poisons are acting. These two things are not explained in this theory. A diagrammatic representation of this theory can be seen here. In the first step, the reactant molecules A and B are approaching the catalyst. It is catalyst. It is adsorbed on the catalyst and the reaction takes place. Here, the reaction takes place, A and B forms a bond. and AB, the product AB is formed. Now the desorption of AB from the catalyst surface, that is separated. Okay, I think it is enough for today. Next day we can see the properties of catalyst and enzyme catalysis.